So we will now do some exercises. So the first one, let XS be a measurable space, Fn a sequence of real valued measurable functions on X. Let E equals set of all x in X such that Fnx is not a Cauchy sequence. Show that E is measurable. So you to show that E belongs to S. Okay, solution. So X belongs to X. So what do you mean by Fnx Cauchy? So that means for every epsilon positive, there exists a capital N such that for all Nm greater or equal to capital N, mod Fnx minus Fmx is less than epsilon. Okay, so so what do you mean by X belongs to E? That means Fnx not Cauchy. So we have to take the contrapositive statement of whatever we have written here. So that means there exists an epsilon greater than 0 such that for every n in N, there exists K and L greater or equal to N such that mod Fkx minus Flx is greater or equal to epsilon. So let us define EKL equals set of all x in X such that mod Fkx minus Flx is greater or equal to epsilon. So Fk, Fl are measurable, so the difference is measurable, absolute value is measurable, and therefore this set is measurable. So now what do you mean by E? E is nothing but union overall epsilon greater or equal to 0 because there exists an epsilon such that for every n, so n equals 1 to infinity, union KL greater or equal to M EKL. Okay, so this of course can be written as union R greater than 0, R rational, intersection n equals 1 to infinity, union KL greater or equal to N EKL. Why? Because every element in the first set, if you take an R which is less than epsilon, will already be in, so call this EKL of epsilon, this is EKL of R. Okay, so EKL of epsilon. So if it's bigger than epsilon, it will be bigger than R. There's a rational which is greater than that, and therefore since it's rational which is less than epsilon, so it will definitely be in this set. Conversely, this is a subset of this, that is obvious, and therefore these two sets are equal. Now here you have everything is countable, rationals are countable, n equals 1 to infinity, KL greater or equal to N, all these are countable sets and they are all in S, and therefore this belongs to S, and therefore it is measurable. 2. X S mu measure space. Fn measurable functions, fn goes to f almost everywhere in X. Does this imply f is measurable? Solution: no, it does not imply that f is measurable. So we have shown that if fn converges to f everywhere, then it is f is measurable. But if fn converges to f almost everywhere, then it need not be measurable. So let assume mu is not complete. Then there exists a E such that mu E is 0 and f contained in E, f not in S. Okay. So now you take fn equal to 0 for all n. Okay. And you take f equal to chi of capital F, which is 1 on f and 0 outside. Okay, so then what happens? Fn x converges to f of x for all x in E complement, because outside E chi of f is 0 and fn is anyway 0, and therefore you have this. And therefore this implies that fn converges to f almost everywhere, but f is not measurable. Three, let Xs be a measurable space. Let f from x cross 0 1 to r be a function such that for every y in 0 1, the map x going to f of xy is measurable, and for every x in x, the map y going to f of xy is continuous. Because we can talk of the continuity, it's 0 1 here and r on the other side, so we can talk of the continuity. Define h of x equals minimum over y in 0 1 f of xy. This is well defined, because for every x, y going to fxy is a continuous function defined on the closed interval 0 1, and therefore 0 1 is a compact interval, and therefore f attains its minimum, so the infimum is actually a minimum. Show that h is measurable. So solution: so h of x equals minimum of f of xy, y in 0 1. So let us say g of x equals infimum r in 0 1, r rational, f of xr. Then we claim h is equal to g. So obviously you are taking the minimum over all y's, and here you are taking only the infimum over the rationals, and therefore h of x is less than or equal to g of x by definition. Now minimum is attained, so let y naught belong to 0 1 such that h of x equals minimum y in 0 1, f of x y equals f of x y naught. Let Rn converge to y naught. Then g of x is less than or equal to f of x Rn which converges to f of x y naught equal to h of x, and therefore this implies g x is less than or equal to h of x. The other side we had h of x less than or equal to g of x, and therefore we have that h equal to g. Now let Sn be a numbering of all rationals in 0 1 and you define Fn of x equals f of x Sn, and therefore this is Fn measurable for all n. Then h of x equals minimum over all n, or Fn of x. So this is by the first part. Given any fixed real number, f of x, x going to fx is a measurable function. Okay, so this h of x is now infimum n Fn of x, and this implies we have already seen that h is measurable. Let f from R to R be Lebesgue measurable. Show that there exists a G Borel measurable such that G equals F almost everywhere. So given any Lebesgue measurable function, we can find a Borel measurable function which is equal to it almost everywhere. So solution. This method we will use very often in integration theory. So we will first prove it for characteristic functions, then for simple functions, then use a limiting argument to prove it for an arbitrary measurable function. Okay, so first let f equals chi e Lebesgue measurable. Then there are several equivalent characterizations of Lebesgue measurability which we have seen. One of them is there exists a f sigma set, f contained in E, and m1 of E minus f equal to 0. So f is Borel measurable because it's a f sigma set, it's a countable union of closed sets, and therefore this implies that G equals chi of f is Borel measurable. Now what is the set of all x in R such that fx is not equal to gx. Now outside E, both of them f and g are 0. Inside f, both of them are 1, and therefore you have that this is contained in E minus f. And m1 of E minus f equal to 0. So set of our measure f not equal to g is equal to 0, that is f equals g almost everywhere. So this is true for a characteristic function. So second step, let us take f to be a simple function. So sigma I equals 1 to k alpha I chi of ei, ei Lebesgue measurable, and ei's are all disjoint, because we can always rewrite a simple function in terms of disjoint sets. Okay, so then this implies, so now you take fi, f sigma set, fi contained in ei, and m1 of ei minus fi equal to 0, and you define g equal to sigma I equals 1 to k alpha I chi of fi. Then g is Borel measurable, and now what about the set g not equal to f? Now these ei's are all disjoints and fi's are contained inside the gi's, and therefore this is nothing but contained in union ei minus fi, and therefore measure of g not equal to f is equal to 0, because each one of this is 0 and you have a finite union. By subadditivity, the measure has to be 0. 3. Let us take f, a non-negative measurable function. Then we know there exists phi n 0 less than or equal to phi n simple, and phi n increases to f. So let Gn be Borel measurable, Gn equal to phi n almost everywhere. So let En is set of all set where Gn is not equal to phi n, and mu of m1 of En is 0, implies m1 of union En n equals 1 to infinity is also equal to 0. And then what is defined f equals union n equals 1 to infinity En complement, which is equal to intersection n equal to 1 to infinity En complement. Now you define G equals supremum over n Gn. So Gn's are all Borel measurable, you are taking the supremum, so this implies that G is Borel measurable. Now m1 of f complement equals m1 of union En, and that's equal to 0, and on f we have G, if x is in f, then it's in all the En complements, and so for every n, Gn equal to phi n for every x in f, for every n, for every x in f. And since phi n increases to f, this means that Gn increases to f on capital F, that is G equal to f on capital F. And F complement is of measure 0, so G equals F almost everywhere. Fourth, F measurable function. So F you can write as F plus minus F minus, and then you have H1, H2 Borel, H1 equal to F plus almost everywhere, and H2 equals F minus almost everywhere, and then you define G is equal to H1 minus H2. Then this implies that G equals H F almost everywhere. That completes this problem. So this is a technique which is very useful, and therefore that is why the fact that a non-negative measurable function is the increasing limit of continuous simple functions is a very important result. Okay.